Hello and a very good day to all. My name is Hazwan and I will be presenting paper ID number 24, which the topic is control of thin McKibben muscles in an antagonistic configuration. So first of all, let me introduce what thin McKibben muscles are. So thin McKibben muscles are a type of actuation system of the variety of actuation systems of soft robotics. These muscles are under the category of pneumatic artificial muscles, and they consist of an elastic membrane surrounded by sleeving and is actuated pneumatically. From figure 2, it can be seen that the elastic membrane, which is the inner rubber tube, is made of silicone, and an outer sleeve is braided with a certain braiding angle. When this muscle is pressurized by high pressured air, the muscle expands radially and contracts axially, producing a force for actuation. So this muscle only actuates in a unidirectional motion where it can only contract and does not expand. But in order for the muscle to be used in a bidirectional motion, an antagonistic muscle, such as in figure 3, is introduced, where one muscle contracts while the other muscle relaxes. And this is also when changing direction, a muscle is going to contract while the other is going to relax, which is the antagonistic muscle. So the advantages of pneumatic artificial muscles are high power to weight ratio, high compliance, and also safe interaction with the environment. In 2013, thin McKibben muscles were developed in order to solve problems of conventional McKibben muscles, where the thin McKibben muscles were more flexible, compact, and also more lightweight. There have been many applications for thin McKibben muscles developed recently, which consist of application in robotics, continuum manipulators, wearable devices, and also rehab. So these are a few applications of thin McKibben muscles which are in antagonistic configuration. A review was conducted on existing research in thin McKibben muscles. From the review, it is found that the research area of thin McKibben muscle is comprised of development, enhancement, control, and characterization. It is also highlighted that the most of the applications use more than one muscle in antagonistic configuration. Although the research in thin McKibben muscle has been showing an uprising trend from 2016 until 2020, the area of control of thin McKibben muscle has received the least attention from researchers, limiting its potential abilities. Controlling pneumatic artificial muscles is a very challenging task. This is due to the muscles inheriting highly nonlinear characteristics such as hysteresis and also dead zones. The muscles also inherit perimeter variations. This leads to difficulty in obtaining an accurate model. Hence, it is very challenging to control pneumatic artificial muscle driven robots with high accuracy. Suitable control strategy is needed for the thin McKibben muscles. This comprise of model-based techniques and also data-driven techniques. Since model-based methods have strong dependency on dynamic model, which is very difficult to obtain for thin McKibben muscles, a data-driven control strategy is designed where data-driven control strategy uses the input-output data of the system and does not need an accurate model of the system. The PID is the most well-known data-driven controller that is used in 95% of practical industrial processes. Firstly, the thin McKibben muscle platform is developed by replicating the index finger of a real human at MCP joint. Then, system characterization is done by inserting different PWM duty cycles from 0% to 47%. Next, the controller is designed and tuning is done. It is then evaluated, and if satisfactory results are achieved, then this marks the end of the experiment. The thin McKibben muscle platform is replicated in terms of bones, joints, muscles, tendons, ligaments, and also tendon sheets. When the desired set point is set, the controller produces an input control signal of 0 to 100% duty cycle PWM to the analog voltage module, where it converts it to analog voltage from 0 to 10 volts. This is sent to the pneumatic regulator, which converts it to pressure from 0 to 0.5 megapascal to the thin McKibben muscle, hence produces contraction and also force. This moves the length of the thin McKibben muscle platform, and the angle of the joint is measured by the IMU. A PI controller is modified to be suitable for the thin McKibben muscle platform, which is antagonistically controlled, where a mode selector is used, F and G, in order to determine whether flexion muscle actuates or extension muscle actuates. Then, dead zone compensation is done by adding parameters Fs and Es. Last of all, the control parameters Kp and Ti are separated for flexion and extension muscle. Tuning is done using Ziegler-Nichols tuning method, and later fine-tuned with a large amount of experiments to obtain better tracking performance. The experiment is conducted by inserting a sinusoidal reference with amplitude of 45 degrees and frequency from 0.01 Hz to 0.07 Hz, incremented by 0.01 Hz, and a step response of amplitude 45 degrees. This is done in using MATLAB with a sample time of 0.01 sec. So this is the thin McKibben muscle platform, and is able to produce flexion and extension motion with the help of flexion and extension muscle in antagonistic configuration. From inserting different values of PWM into the system, it is found that the system inherits highly nonlinear characteristics, and the figure displays large dead zone in the system. This leads to difficulties in obtaining an accurate dynamic model. Therefore, a data-driven control, which is the PID, is desired. From the experiments conducted by injecting a sinusoidal reference, it is found that the PI controller with antagonistic mode selector is unable to handle large dead zones. And by adding the dead zone compensation, which is the ES and FS parameters, it shows major improvement in the tracking performance of the TMM system. The performance is then enhanced by separating the control parameters to form the antagonistic PI controller, which is shown by the better mean square error accuracy compared with the PI controller with antagonistic mode selector and also with dead zone compensation. The API controller is then tested on a step input for extension muscle and also flexion muscle. From the experiment, it is found that the API controller is able to achieve a low steady state error of below 0.07 degrees and also a small rise time of less than 0.5 seconds for both flexion and also extension muscle. From the results, it can be concluded that the thin McKibben muscle platform has the ability of flexion and also extension at the MCP joint, And the design of the thin McKibben muscle platform provides a platform for other control schemes to be implemented in the area of antagonistic thin McKibben muscle applications. The proposed antagonistic PI controller has the advantage of simplicity, high accuracy, and fast rest time as dissipated in the experiments. An interesting future work is to use machine learning techniques such as artificial neural networks in the tuning of the API controller in an online manner to address the issues of parameter variation and also highly nonlinear characteristics of the thin McKibben muscle system in an antagonistic configuration. Here is shown the list of reference used in order to conduct this study. With that, thank you very much for me.